Okay, so now we're looking at a more interesting circuit with capacitors. This is what we call a charging RC circuit. So this time we have a capacitor and a resistor, but in addition we have a battery here connected in series with the capacitor and the resistor, and we have a switch. So as usual, um, well, first of all, we could do many different type of cases, but we'll focus on a case where the capacitor here has no charge to start with. Okay, we could also do problems where we have charge on the capacitor, but those are a bit more difficult. So we start with a capacitor which is initially uncharged, and as usual, we're going to define t equals 0 to be the instant when we close the switch. So we close the switch, and we are going to look at what happens to the circuit. Okay, so now we have just closed the switch here, and you can tell what will happen. So as you close the switch, the battery here is going to push the current in this direction here, right? Because of the polarity of the battery. So we have a current going that direction here. That will move positive charges on this side, on this plate here, or the capacitor, and we're going to accumulate negative charges on the other plate here. Now that we have the current, we know the polarity of the resistor. You have a plus here and minus here because the current always enters the positive side, comes out of the negative side. By the way, this direction here is the direction of the correct current here because we can tell here that the current is going this way. And then we have that we'll have positive charges on this plate of the capacitor and negative charges here. And for the battery, we know that the polarities are plus on this side and minus on this side. Okay, now we have the polarities everywhere. We're going to work out what happens to everything on the circuit. Well, first, if you focus on the charge on the positive plate here, you know that you're going to start with a zero charge because it's initially uncharged, and that charge is going to increase with time. But as time passes, as you add more and more charges here, it gets more and more difficult for the battery to add additional charges. So you expect the current to start high and then to decrease as it gets more and more difficult to add charges. And if you look at the charge here, it starts at 0, it will increase, but it will go to an asymptote. It will level off to a maximum value after a long time. So the charge here increases for a while, then reaches a maximum value, and the current here starts very large and decreases, and goes to 0 if you wait a long time. Okay, we can guess all of that, but we're going to actually we're going to work it out using the equations. So now that we have the polarities here, we apply the loop rule. I can start from anywhere I want, but let's say I start from this point here, and I'll choose to go clockwise. Okay, it's totally conventional. Like you could go the other way, you'll get the same equation. So if I go this way here, and I add all the voltages. So here the potential decreases by an amount equal to minus E, the EMF. So and I keep going this way here. As I go here, the potential increases by an amount equal to delta V across the capacitor. I keep going like this here. The voltage here, the potential increases again, so I have a positive voltage equal to the voltage across the resistor, and I'm back to initial point, so the sum here must be 0. That's it. That's the equation we get from the loop rule. Okay, now to make some progress, we can go and rewrite that using the fact that the voltage across the capacitor is always given by if you look at the absolute value of the voltage across the capacitor, it's always given by the charge on the positive plate divided by the capacitance, and the voltage across the resistor is R times I. So you can rewrite this equation in this form. Okay, this is the voltage across the capacitor, QC over the capacitance, and this is the voltage across the resistor. That's our equation. Now to make more progress, we need to rewrite the equation in terms of just one function. Okay, the EMF here, E, the capacitance C, and the resistance R are constant, and I assume that they're given to us. What is unknown here is the function QC of t and I of t. So before we can solve this equation, we have to relate I of t to QC of t. Now remember, then when we have a circuit, the current is always given by the derivative of the charge in the wire as a function of time. Now this time, because the capacitor is charging, so if you take a cross section here, let's say a given point here, you measure the charge that flows here as a function of time, you take a derivative, you get the current. But as the charges flow here, the charge on the positive plate is increasing in time. Remember the current here, the way we define the current here is always positive. This is always positive here. And in this circuit, the charge here on the positive plate is also increasing in time. So dqc dt is also positive. So because the capacitor is charging, we have that the derivative of the charge in the wire is equal to the derivative of the charge on the positive plate with respect to time. So they're equal. When we add the discharging circuit, we add an extra minus sign here, because when you have charges flow in the circuit, when it's discharging, the charge on the positive plate was decreasing in time. This time here, the charge on the positive plate is increasing in time, so those two derivatives here have the same sign. They're both positive. Okay, so I of t is dqw dt, but in this case is equal to dqc dt. Okay, so we have this equation. When we add the discharging circuit, we add the minus sign here. Okay, so now that we have that, we have this equation here. So all I did was to replace I of t by, you see I of t here I replaced by dqc dt. Now we have a differential equation for what? For the function qc of t. So we have to solve this differential equation. The way to do that here is just to isolate everything that depends on QC on one side of the equation, everything that depends on time on the other side, and the only thing that depends really directly on time is dt here. I mean, QC is a function of time, but we can stop for a second writing we remember this is just it tells us that in the end we'll have a function of time, but the only place where time appears explicitly in this equation is in the dt here. So I just have to isolate dt and qc. So just to remind you what we're trying to do, we're trying to find the function qc of t in terms of the three constants of the circuit, which are the resistance, the capacitance, and the EMF of the battery. But when we solve the differential equation, you know you're going to have an unknown constant, arbitrary constant. So to fix that, we need an initial condition. We need to know the charge at some time. And in our case here, we're going to use the initial condition that the charge on the positive plate at t equals 0, we set that equal to 0. That's our initial condition. That will help us fix the constant that we get from when we integrate. Okay, so going back to here, I just isolate everything that depends on QC on one side and everything that depends on time, which is just dt on the other side, and I get this. Okay, so on this side I have the QC here, and then I have the dt on this side here. Now you have a constant here, you have minus 1 over RC. It's totally up to you if you move it on this side or you leave it on the other side here, but it's easier, in this case, it's easier to write the equation in this form. Now what do we do next? We have everything that depends on QC on one side, on time on the other side. So what we do next, we integrate both sides. So if you integrate this side here, what you get is you get ln of QC minus CE. Remember, CE is just a constant. So again, think of that as, let's say you are integrating dx over x minus 5, let's say. So the integral of dx over x minus 5 is just ln of x minus 5 plus a constant of integration. So you integrate that here, you just get ln of qc minus ce plus a constant of integration. You integrate this side, you just get minus 1 over c times the integral of dt, which is just t, plus a constant of integration. So we get this. Integrating both sides, we get this equation here. Next step is just to, we want QC as a function of time, so it's just to isolate QC as a function of time, moving things around. I won't show all the steps, but then it's fairly easy to get QC isolated. And then once you have that, you'll have a constant that would be left in your arbitrary constant left in the equation, and then you have to impose this. You have to impose that when you set t equals 0, you want QC to be equal to 0. That will fix the constant. And the final answer is that you get this. You should get this. QC as a function of time is given by this equation, CE times 1 minus E to the minus T over tau. And as for the discharging circuit, tau is still given by R times C. Okay, and that's called the time constant again. Now, to check some values of the functions here, it would be useful to remember two special cases. we often check equations at t equals 0 and at t equals infinity. For t equals 0, you encounter, no, if you set t equals 0 here, you get e to the minus 0, which is e to the 0, and we'll need to use that e to the 0 is just 1, right? Anything raised to the 0th power is 1. We also often want to check the equation when t equal to infinity. If you set t here goes to infinity, this becomes e to the minus infinity over a constant, so it's just e to the minus infinity. So what is e to the minus infinity? Well, that's easy because you can write that as 1 over e to the infinity. Now e is a number, now it's 2.718, it's a number larger than 1. So e raised to the infinite power, that just gives infinity. So this is the same as 1 over infinity, which is 0. Strictly speaking here, no, don't show that to mathematicians because they will cringe. Really, I'm really taking a limit here. I should write that as e to the minus t and write the limit as t goes to infinity. But it's understood here, it's really, I mean e to minus infinity in the sense of a limit. Okay, so given these values here, we can check. If you set t equals 0 in this equation here, so what do you get? You get CE times 1 minus e to the 0. So you get CE times 1 minus e to the 0, which is 1, and that gives 0. Of course, no, as it should, right? That's a condition we impose to solve the equation. Okay, what about at t equals infinity? So you start with no charge at t equals 0, which is, we know it should be like that. If you wait a very, very long time, we know the charge will reach a maximum value, but what is it equal to? So we just look at t equals infinity, and you plug t equals infinity here, you get 1 minus e to the minus infinity. But e to the minus infinity is 0. So you just get CE times 1 minus 0, so you get CE. So this is the charge reached after an infinite time, and this is basically the maximum charge that will accumulate on the positive plate of the capacitor. So sometimes people replace CE in those equations by Qmax. They call that Qmax. So the curve looks like this, right? You build up the charge and you reach an asymptote. Strictly speaking, you reach CE just after an infinite amount of time. But in practice, you get very, very close after a few times constant. By the way, here, this is given as a percentage. So really here, they mean 100% of Qmax. And Qmax is C times E. So really here, no, this is really, the 100 here really means 1 times CE. Here 90% means 0.9 times CE, 0.8, and so on. Okay, so those are fractions of Qmax, which is CE. There is one special point here marked, which corresponds to a percentage of 63.2% of Qmax, and that occurs after one time constant. I'll come back to that in a minute, but we'll get that number here. We'll see where that number comes from in a minute. Okay, so that's the behavior of the charge on the positive plate. Now, okay, let's ask the following question. How much charge is on the capacitor if you wait one time constant? Remember, time constant is R times C, and it's a number in seconds. For a given resistance and capacitance, this is a time in seconds. So if you wait a time equal to one time constant of that circuit, okay, the time constant depends on the R and C you're using, but if you wait one time constant, how much charge is on the positive plate? So in terms of equation, if we turn that question into a mathematical equation, we're asking what's the value of QC of t when the time is equal to one time constant, 1 tau. So we just plug that in the equation. We go back in the original equation, and I just replace t by tau, right? I've set t equal to tau in this equation here. So when t is equal to 1 tau, you get CE times 1 minus e to the minus tau over tau, but that's just e to the minus 1. So we get this. Okay, so this is a number. 1 minus e to the minus 1 is a numerical number. You use a calculator, you calculate that, and you find that 1 minus e to the minus 1 is about 0.632. So we get 0.632 times CE. But remember, CE is the maximum charge. So we get about 63.2% of Qmax. So this is telling us that if you wait one time constant, you'll have 63.2% of the maximum charge that will have accumulated on your positive plate. Okay. Now you can calculate at any other time. For example, you can ask, okay, if I wait 2 time constant, then you'll get closer to Q max. But how close are you going to get? Well, you just set t equal to 2 tau in your equation. So if you go back in the equation here, if you want at 2 tau, you'll have CE times 1 minus e to the minus 2 tau. You'll have a 2 here, 2 tau over 2. So here you get CE times 1 minus e to the minus 2 now. If you calculate that, 1 minus e to the minus 2, you get 0.865. So you get about 86.5% of Qmax. That makes sense. We wait longer, we're getting closer to Qmax. But you see it's an asymptote. You get closer, but it takes longer and longer to get closer and closer to Qmax. So you have this curve that we saw before. Okay, now you have QC of t. And once you have QC of t, you can calculate everything about the current. For example, you can find the current and all the voltages. But I'll show you that in another video, in the next video. Thank you.